Hello everyone, today I'm going to discuss with you the cardiac tachography. Firstly, we will begin with the physiology of fetal oxygenation. Fetuses, unlike adults, are not exposed to atmospheric oxygen when confronted with hypoxia. Adults can increase their rate and depth of respiration to enhance the intake of oxygen so as to maintain positive energy balance and protect their myocardium. In contrast, fetus, when exposed to hypoxia, cannot increase its oxygen supply, and therefore it will decrease its heart rate in order to reduce the myocardial workload to maintain a positive energy balance. This reflex response to decrease the heart rate to protect the myocardium against hypoxic or mechanical stresses heard as a deceleration during fetal heart rate monitoring. Placentation. What is the impact on fetal oxygenation? What is the placentation do, or what is the impact of placentation on fetal oxygenation? From 12 days of life until full term, the embryo and the fetus obtain their nutrition and oxygenation from maternal circulation to survive and grow. There, it is mandatory for the well-being of an embryo and a fetus to have optimum uteroplacental circulation as well as adequate placental reserve. This process of establishing an effective uteroplacental circulation is complex and require a synergy between the trophoblastis of embryo and the endometrium of the mother. Normal placentation. The physiology of normal placentation. Fertilization occurs in the fallopian tube, and the fertilized ovum enters the uterine cavity around the third day as a morula, 12 to 16 blastomeres. The inner cells of the morula differentiate into an inner cell mass that will form the tissues of the embryo. In contrast, the surrounding cells differentiate into the outer cell mass that will give rise to the trophoblast, which will subsequently form the placenta. The accumulation of fluid occurs rapidly, forming a fluid-filled cavity within the morular blastocele and thereby creating the blastocyst. During this time, the early embryo receives its nutrition and eliminates waste produced by a simple process of diffusion through the zona pellucida. About the sixth day, the cells form the trophoblast, begin to penetrate between the endometrial cells of the uterus. The process of implantation is usually completed by the 10th or 11th post-ovulatory day. By that time, the original trophoblast surrounding the embryo has undergone differentiation into two layers, the inner cytotrophoblast and the outer syncytial trophoblast, which will invade the endometrium and subsequently form the placenta. The growth of the embryo and the disappearance of the zona pellucida induce a need for a new and more efficient method of exchange of nutrients. This need is fulfilled by the uteroplacental circulation that allows a close contact to exchange gases, and within the syncytial trophoblast aids this need is fulfilled by the uteroplacental circulation that allows a close contact to exchange gases and metabolites by diffusion between maternal and fetal blood. The formation of lacunae within the syncytial trophoblast aids in the development of an efficient uteroplacental circulation. The uterus at the time of implantation is in the secretory phase and secondary to the rise in concentration of progesterone. The stroma cells of the endometrium accumulate glycogen and get enlarged. On day 12, the syncytial trophoblast secretes enzymes that enable the endometrium is invade the endometrium and hormones that help to sustain ongoing pregnancy, beta CTG. Enzymatic corrosion of uterine glands liberates their contents for nutrition. Enzymatic corrosion of uterine gland liberates their content for nourishment of embryo together with the glycogen provided by the stromal cells. Maternal vessels at implantation site, branches of spiral arteries and endometrial veins, dilate and form internal sinusoids. The erosion of sinusoids by the syncytial trophoblast in maternal blood bathing the lacunar network, allowing the exchange of gases and nutrients. Thus, a primitive uteroplacental circulation begins by the end of the second week with the anastomosis between trophoblastic lacunae and maternal capillaries. These cellular changes, together with an increase in endometrial vascularization, are known as decidual reaction. It commences at the implantation site and spreads throughout the entire endometrium within a few days. And this newly formed layer is called the decidua. As the trophoblast continues to invade more and more sinusoids, maternal blood begins to flow through the trophoblastic system. The cytotrophoblast, meanwhile, proliferate and forms protrusions penetrating into the syncytial trophoblast all around the blastocyst. These extensions are known as primary villi. On day 16, after being invaded by the chorionic mesoderm, secondary villi are formed. This is followed by the development of blood vessels within the chorionic mesoderm, leading to the formation of tertiary villi on day 21. Secondary and tertiary villi are often termed as chorionic villi, and hypoxia or lower tissue oxygen content in the decidua is critical for normal trophoblast invasion and formation of these villi. The embryonic circulation is anatomically separated from the maternal circulation by the endothelium of the villus capillaris, the connective tissue in the core of the villus, a layer of cytotrophoblast, and a layer of syncytial trophoblast. By the end of fourth week, tertiary stem villi surround the entire chorion and establish contact with the extraembryonic circulatory system, connecting the placenta and the embryo. This ensures that nutrients and oxygen are supplied to the fetus, and metabolic waste products are removed when the fetal heart begins to start beating. Impact of placental reserve impact of placental reserve on fetal growth and well-being. If the placental reserve is low, uteroplacental sinuses are smaller during the antenatal period. The fetus might have restricted growth to supply oxygenated blood to the vital organs. During labor, the onset of uterine contraction might lead to rapid development of hypoxia and acidosis due to the compression of branches of the uterine artery by the contracting myometrial fibers. Similarly, an injudicious use of oxytocin may increase the frequency, duration, and strength of uterine contractions and thereby reduce the perfusion of uteroplacental sinuses, leading to the development of hypoxia and metabolic acidosis. Similarly, in diabetic pregnancies, hyperplacentosis may reduce the amount of placental pools available for gaseous exchange, leading to a rapid development of hypoxia and acidosis. What is the rapid development of hypoxia and acidosis? What is the fetal? How fetal adapt the hypoxic intrauterine environment? The fetus lives in a relatively hypoxic intrauterine environment with an arterial oxygen saturation of 70% prior to the onset of labor. During labor, intermittent uterine contractions may further reduce fetal oxygen saturation down to 30%. Unlike adults, a fetus has 18 to 28 grams of fetal hemoglobin, which helps to increase the oxygen carrying capacity of fetal blood. In addition, unlike adult hemoglobin, fetal hemoglobin has increased affinity for oxygen. This results in the binding of oxygen molecules at higher partial pressures of oxygen and the releasing of oxygen rapidly at very low oxygen tensions. This enables the fetus to maintain adequate oxygenation of the central organs even when it is not exposed to external environment. Moreover, an increased level of fetal hemoglobin acts as an effective buffering system in the presence of metabolic acidosis to help avoid fetal neurological damage. The fetal circulatory system consists of ductus venosus and foramen ovale, both of which preferentially shunt oxygenated blood from the umbilical vein to the heart and the brain. In addition, ductus arteriosus diverts the blood from the pulmonary artery to the descending aorta by passing non-functional lungs. This vascular arrangement enables the fetus to supply the central organs with relatively well-oxygenated blood as compared to the peripheral tissues in order to rapidly distribute the blood to vital organs. Unlike in adults, fetal myocardium beats at a higher rate, 110 to 160 beats per minute. Abnormal placentation, a failure of trophoblast invasion into uterine endometrium would result in inadequate formation of placental lacuna. This would lead to a reduction in the size of pools of oxygenated blood within the uterine venous sinuses. Therefore, there may be intrauterine growth restriction during the antenatal period to divert available oxygen and nutrients to the vital organs. During labor, with the onset of uterine contractions due to compression of the branches of spiral arteries, there may be a rapid development of hypoxia and acidosis. In addition, placental disorders such as infection, vasculitis, vasculopathy, and failure of trophoblastic invasion, like preeclampsia, may lead to reduction of placental pools, resulting in uteroplacental insufficiency. The four major causes of abnormal placentation is infarction, vasculitis, vasculopathy, and failure to trophoblastic invasion, like in preeclampsia. Fetal response to hypoxic stress. How fetal responds to hypoxic stress? A response to hypoxic stress, fetus attempts to safeguard the positive energy balance of the myocardium to avoid myocardial hypoxia and acidosis. As the fetus, unlike adults, cannot rapidly increase oxygen levels by increasing the rate and depth of respiration, it decreases the myocardial workload by reflex slowing of the fetal heart rate. This is termed deceleration. If this reflex response to hypoxic stress is insufficient to maintain oxygenation of the central organs, brain, heart, and adrenal glands, the fetus would conserve non-essential activity by stopping movements, leading to a loss of accelerations in the cardiotograph trace. If intrapartum hypoxia progressed further, a fetus would release catecholamines, adrenaline, and noradrenaline to increase the heart rate, then increasing oxygenation from the placental bed and also causing peripheral vasoconstriction to divert blood from non-essential peripheral organs to central organs. In addition, catecholamines increase breakdown of glycogen to glucose to increase energy substrate to continue maintaining a positive energy balance within the myocardium. This leads to a compensated response, and the fetus would continue to demonstrate a stable baseline fetal heart rate and a reassuring baseline variability from 5 to 25 beats per minute, albeit with continued decelerations and a rise in baseline fetal heart rate. This is followed by the onset of decompensation in the central nervous system, leading to a loss of baseline fetal heart rate variability, followed by the onset of myocardial hypoxia and acidosis characterized by unstable baseline and progressive reduction of the heart rate, a stepwise pattern to death. In summary, a fetus is not exposed to atmospheric oxygen during intrauterine life and therefore develops cardiovascular, metabolic, and hematological adaptation to ensure adequate oxygenation to central organs. Response to hypoxic stress, the only organ the fetus attempts to safeguard is the myocardium, the pump, so as to maintain continuous perfusion to the vital organs. A reflex decrease in fetal heart rate, deceleration, conservation of energy, loss of fetal movements, and release of catecholamines to increase placental circulation, redistribute blood from peripheral organs to central organs, and increase the availability of energy substrate glucose. Failure in any of these mechanisms may lead to the onset of hypoxia and metabolic acidosis, leading to neurological damage or death. Hello students, this is the last of our lecture today. Thank you.